April 1919. A massive steel cylinder navigates the English Channel. It is not moving under its own power. It is being dragged through the heavy seas. This is the Imperial German Navy submarine U-118. It is a Type UE-2 minelaying submarine. The war is over, and the vessel is a surrendered prize. The towing arrangement is under French control, with the French destroyer François Garnier acting as escort, while an ocean-going tug handles the dead submarine on the tow. The ocean weather rapidly deteriorates into a severe gale. The water applies massive opposing forces against the steel cable connecting the two ships. The dynamic shock loads spike violently. The hawser snaps. In a single violent moment, an irreversible step is taken. Control is lost entirely. A vessel displacing more than 1,100 tons surface transitions from a secured transport asset into an unguided steel mass adrift in one of the busiest waterways in the world. The U-118 is a massive machine. It measures 267 feet in length. Its surface displacement exceeds 1,164 tons. It was specifically designed to carry internal mine payloads and to operate safely under extreme ocean pressure. With no crew aboard and no active propulsion or steering, those wartime design strengths no longer serve a commander. They only add mass to the tow. Towing a dead ship in the open ocean requires a precise balance of tension. The line must drag an 1,164-ton mass through resisting water while absorbing the movement of both vessels. In a severe gale, the destroyer can rise sharply on a wave crest as the dead submarine falls into a trough. That opposing geometry turns steady strain into violent shock loading. Once the cable exceeds its tensile limit, it parts, releasing the stored energy into the sea. The commander of the French destroyer Francis Garnier faces an immediate tactical crisis. The English Channel is heavily congested with maritime traffic. The English coastline is relatively near. An unlit, unguided, heavy steel battering ram is loose in the darkness. Recapturing the snapped tow in a severe gale is a physical impossibility. Approaching the thrashing submarine to manually attach a new line would risk the structural destruction of the destroyer itself. The storm is pushing the heavy hull directly toward the populated coast. A massive ship grounding in a completely uncontrolled state poses a severe kinetic threat to civilian coastal infrastructure. The destroyer makes a calculated operational decision. It requests permission to sink the drifting prize before the submarine can become a greater hazard. Permission is reportedly granted, but the surviving accounts are not precise enough to prove every action that follows. Some later accounts describe an attempt to stop the submarine by gunfire. If the destroyer did open fire, the practical problem was not a heroic armored target shrugging off shells. It was the channel itself. A low, dark submarine in a rising gale would have been a poor target, constantly disappearing behind broken water while the escort rolled and pitched through the storm. The available record supports an attempted intervention far more safely than it supports a detailed artillery duel or confirmed hits on the pressure hull. If any gunfire was attempted, it does not produce a confirmed sinking. The attempted intervention fails to stop the hull before it reaches the shallow waters of the English coast. At 12:45 in the morning on April 15, 1919, the blind drift terminates against the English shoreline. The dark mass of the submarine strikes the shallow sand. The geometry of the impact immediately dictates the severity of the crisis. The heavy structure does not wash ashore on a remote stretch of coastline. It drives directly onto the highly populated public beach at Hastings in Sussex. The enormous steel cylinder comes to a complete halt directly in front of the Queen's Hotel. A massive weapon of war is now locked into the exact center of a civilian environment. The kinetic threat of the drifting vessel is over. A new static hazard instantly replaces it. The submarine is embedded parallel to the tidal line. The soft sand beneath the hull yields to the extreme weight, cementing the unpowered machine firmly into the landscape. The grounding turns the beach itself into the trap. Standard maritime recovery relies on deep water to keep most of a vessel's mass buoyant, but the falling tide removes that lift. The submarine's weight settles onto wet sand. Suction and friction build along the long steel hull, converting a floating warship into dead weight. The immediate requirement is to remove the massive obstruction from the civilian town. The structural integrity of the submarine remains largely intact. The initial engineering approach focuses on brute force mechanical extraction. If the hull can be dragged back into deep water, the ocean can restore its buoyancy. Towing from the sea is no longer an option. The shallow angle of the Hastings Beach prevents any heavy recovery ship from approaching close enough to attach a new hawser. The water depth is insufficient. The salvage effort must originate entirely from the land. Local authorities requisition heavy pulling equipment to reverse the grounding. 3 tractors are brought down to the Hastings beachfront. Heavy steel cables are rigged from the landward side of the massive submarine and attached to the rear towing hitches of the motorized machines. The operational plan is simple. Combine the pulling force of the 3 tractors and break the seal holding the hull down. The machines must drag over 1,100 tons of high tensile steel against the severe friction of the beach. The extraction attempt is a complete mechanical failure. The physical mathematics of the stranded geometry defeat the land-based equipment. The 3 tractors throttle up to maximum power. The steel cables pull taut. The immense resistance of the embedded submarine does not yield. The tracks and wheels of the heavy machinery simply dig useless trenches into the soft sand. The cables remain under extreme tension, but the submarine does not shift a single inch. The mechanical refloat attempt is formally abandoned. Standard dragging methods have failed, leaving the authorities with a fixed industrial problem. The submarine cannot be hauled back to sea, and it cannot be left to rust in the center of a populated town. The immediate requirement to eliminate the naval hazard collides with the town itself. On a remote shore, explosive demolition might have broken the wreck into removable sections. At Hastings, below hotels, streets, and the public promenade, the safety perimeter does not exist. The same blast that could break steel could also send shock and fragments into the civilian frontage. The institutional authorities confront a severe operational deadlock. Admiralty engineers must evaluate the force needed to crack a thick naval pressure hull. That force would require concentrated charges, and in this location their effects would not stay inside the wreck. Overpressure could shatter the town front glass, damage weak facades, compromise the nearby hotel, and throw jagged steel or rivets into streets and residential blocks. What might be a clearance method elsewhere becomes unacceptable beside a civilian frontage. The authorities rule out heavy explosive demolition. The fastest, obvious clearance method is removed, leaving the wreck intact on the sand. The extreme engineering durability of the submarine, originally designed to protect a wartime crew from ocean hazards, now entirely protects the stranded wreck from the salvage teams. The restriction forces a slower and more awkward response. The hulk is no longer a simple towing problem, but a stranded, partially flooded machine whose interior cannot be treated as safe. Hatches are opened and inspections are made, but the lower spaces remain dark, wet, confined, and poorly ventilated. In those conditions, damaged electrical spaces and battery compartments can turn from abandoned machinery into a hidden chemical danger. The ban on heavy blasting does not preserve a perfect sealed laboratory. It simply leaves the dangerous interior to deteriorate slowly. Beneath the visible wreck, water, damaged equipment, and poor ventilation create the conditions for a hidden toxic atmosphere. The stranded machine remains physically stationary on the public sand, but the danger inside it is no longer purely mechanical. The internal architecture of the submarine depends on banks of lead-acid batteries to provide submerged electrical power. Those batteries sit low inside the pressure hull, in spaces that are especially vulnerable once seawater begins to enter a stranded wreck. The surviving accounts do not prove exactly which casings, seals, or fittings failed. What they do support is simpler and still dangerous. Seawater and damaged battery spaces appear to have combined inside the hulk, changing an abandoned electrical compartment into a source of toxic fumes. When seawater reaches damaged lead-acid batteries, toxic fumes can form. Contemporary accounts later describe the gas inside the submarine as noxious, possibly chlorine. The safer technical reading is an uncertain buildup of poisonous vapor, not a measured cloud of concentrated gas. The danger comes from confinement and poor ventilation, not from a perfectly airtight hull. With no active ventilation running, heavier than air fumes could collect in the low internal spaces and remain dangerous even after hatches had been opened above. Unaware of the danger building below, local authorities allow the wreck to become a controlled public spectacle. The town clerk receives permission to charge visitors to go aboard the stranded submarine and raise local funds. The stronger evidence points to public access on the deck, with interior visits handled more selectively. 2 local Coast Guards are drawn into that interior duty. Chief Boatman William Hurd and Chief Officer W. Moore guide selected visitors through the darkened spaces before the danger is fully recognized. Each descent takes them into a confined, poorly ventilated atmosphere that may already be contaminated by fumes from damaged batteries. The 2 men have no respiratory protection. They breathe contaminated air inside the wreck before anyone fully understands the danger. Chlorine, if present, is a severe lung irritant. It reacts with moisture in the airways and can damage living tissue. Later accounts of the inquest attributed fatal abscesses in the lungs and brain to exposure to a noxious gas, possibly chlorine. The evidence supports that conclusion, but not a precise medical reconstruction of every internal step. The result is 2 delayed fatalities linked to the stranded submarine. The enormous metal structure has successfully executed a lethal strike against the local population long after the formal cessation of hostilities. The illnesses, not the later deaths themselves, bring the interior visits to an end. Moore dies months later, in December 1919. William Hurd dies in February 1920. By then, the wreck's interior has already been recognized as a dangerous place rather than a harmless curiosity. The suspected toxic atmosphere forces the authorities to treat the interior as dangerous. Any clearance plan that depends on routine work deep inside the hull becomes far harder to justify. The Admiralty is left with the same central problem. The submarine must be removed from the town, but it cannot safely be blasted apart beside the hotel, and its interior cannot be treated as a normal workplace. The military officially abandons the immediate hazard clearance operation. The Admiralty transfers the entire physical burden of the stranded asset to the civilian commercial sector. They formally divest the heavy naval hazard. The extreme constraints surrounding the enormous vessel dictate a complete shift in operational logic. The military firmly accepts that rapid structural clearance is entirely impossible. The unyielding geometry of the site forces a slow industrial resolution. On May 21, 1919, the legal ownership of the massive structure fundamentally changes. The British Admiralty successfully sells the dead submarine to the James Dredging Company. The commercial salvage firm officially purchases the intact vessel for exactly £2,200. This definitive financial contract dictates the new operational mandate. The immediate objective is no longer rapid military hazard removal. The new driving goal is systematic, profitable, and highly controlled industrial scrapping. The civilian engineers inherit the same physical conditions that defeated any simple response. They face a heavy steel hull embedded in soft sand, without the safe option of large explosive demolition beside the town. Their answer is not a single dramatic lift or refloat. It is commercial braking in place. The wreck is reduced gradually for scrap, section by section, using the tools and labor available on the beach. The exact equipment sequence is not securely documented, so the safe conclusion is broader. The submarine is cut down as an industrial object, not recovered as a seaworthy vessel. The daily tidal cycles of the English Channel continuously dictate the strict working schedule. The salvage crews can only attack the deeply embedded lower sections of the keel when the ocean water fully recedes. The heavy tidal surges routinely flood their deeply excavated working trenches. This environmental interference forces the men to repeatedly abandon their active cutting positions and wait for the next low tide window. The cold ocean water constantly degrades their mechanical tools and coats the exposed metal in heavy sand. The wet beach sediment provides a highly unstable foundation for moving heavy lifting equipment. The commercial firm is forced to construct extensive temporary wooden tracks and thick timber platforms to stabilize the heavy extraction winches and solid transport carts. Every severed piece of dense steel must be manually rigged, hoisted, and dragged forcefully across the soft sand without the critical assistance of heavy floating cranes. The surviving record does not prove a deliberate top-down ventilation plan. What it does show is a slow reduction of the stranded hulk on the beach. As the wreck is opened and broken up, the enclosed danger inside loses the same power it had when men were entering confined spaces. The great rigid profile of the submarine is gradually cut away, hauled off, and turned from a single, immovable hazard into separate pieces of scrap. Over months of tidal work, the visible profile of the submarine shrinks. The main hulk is broken up on the Hastings shoreline during the period after the sale, with later accounts placing the principal clearance around 1919 to 1921. The work removes the public spectacle piece by piece. Carts and labor carry the severed material away, and the enormous visual footprint of the naval weapon steadily retreats from the civilian landscape. The final stages of the dismantling operation focus on the deepest and most stubborn elements of the massive vessel. The lowest sections of keel, ballast, and buried framework naturally prove the most difficult to isolate. The original weight of the submarine has driven parts of the lower structure deep into the wet coastal sediment. Salvage crews must keep working against the sand itself, exposing metal, cutting what can be reached, and hauling away the sections that can be economically removed from the tidal zone. The raw materials still represent significant commercial value. Brass fittings, copper wiring, machinery, and heavy steel plates are stripped from the wreck and routed back into the industrial economy. The submarine is no longer treated as a warship. It is treated as salvage, valuable, dangerous, awkward, and slowly reducible. Every removable section becomes another load of scrap, another piece of the once continuous hull separated from the beach. Around the worksite, the tide begins to do what the work crews cannot do cleanly. Sand slides back into trenches. Water softens the scars of cutting, hauling, and excavation. The English Channel gradually smooths the heavily marked stranding ground. Yet the surviving accounts do not support a perfect ending in which every last buried fragment is recovered. The main visible wreck is broken up and removed, but later reports differ over the fate of the deepest keel material. Some accounts describe keel sections being uncovered or removed years later. Others leave open the possibility that buried remnants remain below the beach. The commercial salvage operation therefore achieves the practical clearance that Hastings needed most. The massive visible barricade is eliminated from the waterfront. The public beach in front of the Queen's Hotel is no longer dominated by an enemy submarine. The civilian town reclaims its coastal frontage, not through one spectacular act of destruction, but through months of slow industrial reduction, tide-bound labor, and the steady conversion of a stranded naval machine into scrap. The physical reality of the coastal minelaying submarine is reduced to history, memory, and possible buried traces. An enormous deep ocean naval machine, engineered for pressure, endurance, and war, is defeated not by a final explosion, but by weather, sand, commerce, and human persistence. The severe ocean storm had delivered an uncontrollable kinetic force into the center of a populated environment. The deliberate, methodical application of civilian engineering removed the main threat piece by piece. The public beach returns to its tidal rhythm. The steel predator no longer rules the Hastings shoreline.